All right, today we're going to tackle a topic that trips up so many of us in math, graph transformations. But look, we're not just going to sit here and memorize a bunch of rules. Nope. We're going to treat this like a secret language, a code. And by the end of this, you and we're going to crack it together. Okay, let's dive in. And here it is, the big one, the great mystery, the thing that honestly feels like a typo in every textbook. You see a function, something like f of x minus 3, and your brain just screams, that's got to be left. But then you graph it, and whoosh, it slides to the right. What is going on, right? This one single kind of backward idea is the key to unlocking this whole thing. And this visualizes the problem perfectly. You see the original function right there in the middle, but f of x minus c is, well, it's clearly shifted to the right. It seems totally backwards, I get it. But just stick with me here, because once we decipher the logic behind this, it's not just going to make sense. I promise it's going to feel completely obvious. So, to crack any code, you always start with the easy part first, right? For us, that's what I'm calling the vertical code. This is all the stuff that happens outside the function's parentheses. This part is simple, it's direct, and it's going to build our confidence for the trickier stuff. So, let's start with vertical shifts. When you add or subtract a number from the entire function, from the whole thing, it does exactly what you'd expect it to do. You add a positive k, the whole graph just goes up. You add a negative k, or, subtract a number, and the whole graph slides down. It's direct, it's intuitive, love it. And hey, let's just look at a quick proof. We'll start with the basic square root function. Then we graph the square root of x plus 3. And look at that. Every single point on that original curve has just been lifted straight up by 3 units. So the first piece of our code is confirmed. See? Easy, right? Okay, so what happens if we multiply the outside of the function by some number? We'll call it a. Well, this number a is kind of like a volume knob for the graph. It controls the vertical stretch. And if a happens to be negative, it does something even more dramatic. Just look at the contrast right here. On the left, we're multiplying by an a that's bigger than 1. And you can see it makes the graph taller. It's stretching it vertically. But on the right, a negative multiplier completely flips the entire function over the x-axis, just like a perfect reflection in a pond. So the big takeaway for this vertical code is really simple. Anything happening outside the function's parentheses directly changes the y-value, just like you'd think it would. It's a what you see is what you get kind of system. So with that locked in, let's go tackle the tricky part. All right, team, this is it. We're heading inside the parentheses. This is where that whole minus means right mystery lives. I know it's confusing, but we are about to unlock a whole new way of thinking about this that I swear is going to make it all click into place. This is the breakthrough. This idea, which actually came from a fantastic discussion I saw online, it changes everything. What if I told you the function isn't moving at all? What if instead we're moving the entire world underneath it? I want you to imagine this. The graph of f of x is drawn on a clear sheet of plastic, and you're holding it perfectly still, okay? Now, for f of x minus 3, what you're actually doing is sliding the grid paper underneath it 3 units to the left. So from the grid's point of view, what happened to the graph? It now looks like it's 3 units to the right. The graph never moved. Your perspective did. Okay, here's another way to think about it that I really love. The function f of x minus 3 has a handicap. To get the same output that f of x gets at 0, our new function needs an x value of 3. So to hit that same target y value, our x has to catch up by being 3 units bigger. And where is x equals 3? Well, it's 3 units to the right of 0. So now we can finally state the rule with total confidence. When you see f of x minus h, you're shifting the graph to the right. When you see f of x plus h, you're shifting it to the left. The input x is always doing the opposite of what you see in the parentheses, just to compensate and get back to that original value. And right here, this is the visual proof. On the left, you've got the absolute value of x. Its sharp point, its vertex, is sitting right at 0. But when we graph the absolute value of x times plus 3, look where the vertex goes. It moves to negative 3. That's a perfect 3-unit shift to the left. See? The counterintuitive code? It's cracked. Okay, so we've decoded the vertical moves, we've decoded the horizontal moves, but what happens when a function has both? Well, it turns out the order you apply them in can be the difference between the right answer and a graph that's totally wrong. This right here is the master key. You know, the rule for order is actually pretty simple. Think of it like this. All the vertical transformations are in their own club, and all the horizontal ones are in another club. You have to be careful about the order of operations within each club, but you can do all the horizontal stuff before, after, or even in between the vertical stuff. They just don't mess with each other. This classic Jack and Jill example shows exactly why this order matters. So imagine they're both trying to graph negative x squared plus 2. Jack reflects the parabola over the x-axis first, then he shifts it up 2 units. Perfect, he got it right. But Jill, she shifts it up 2 units first, and then she reflects that entire shape over the x-axis. She ends up with a completely different graph. This proves it. When you have 2 vertical moves, like a reflection and a shift, the order really, really matters. We have all the keys now. We understand the vertical code, the horizontal code, and we understand the importance of order. So I think it's time to put it all together and crack a complete function from start to finish. Let's do it. Here's our target, the absolute value of x plus 3 all minus 2. Our plan is super simple and it follows our master key. We're going to start with the parent function, then we'll handle the horizontal transformation that's inside the parentheses, and finally, we'll apply the vertical transformation that's hanging out on the outside. So step 1, our blank canvas. This is just the basic untransformed absolute value function, y equals the absolute value of x. The classic V-shape, you know it, with its vertex sitting right there at the origin. Now for step 2, we apply that horizontal code. We look inside the absolute value bars and we see a plus 3. And we know now that that's our counterintuitive signal to shift the entire graph 3 units to the left. So now the vertex is sitting at negative 3. And for the final step, we look at the vertical code. We look outside the function and we see that minus 2. This is the easy, intuitive part. What you see is what you get. So we take our already shifted graph and just pull the whole thing down by 2 units. And there it is, the final graph perfectly cracked. So there you have it. What started out as this really confusing, kind of backwards rule is now a system, a code that we can actually read and apply. You now have the tools to look at any function and see the story of its journey from a simple parent graph. And to make this even easier, just think of this table as your master decoder ring. Seriously, it has every single rule we've covered today all in one place. You've got the intuitive outside vertical moves, the counterintuitive inside horizontal moves, and all the reflections. This is your cheat sheet for becoming an absolute master at this. So I want to leave you with this one final thought. We started this whole thing trying to understand why a minus sign moves a graph to the right. But what we discovered is that maybe the graph isn't moving at all. Maybe we're just learning how to shift our own frame of reference. It's kind of cool to think about, right? Thanks for tuning in.